Okay, folks, let's begin our next lecture. This time we're looking at sedimentary rocks. So we're going to start talking about the next part of that rock cycle in some detail. We're going to look at sedimentary rocks, much like this one that you see in the background here. I'm going to start to answer questions like, how can we tell when and how this rock formed by looking at it? What was the environment like when this rock formed? Why do we have all these sort of linear looking features that are trending in particular directions? They're all oriented together. What's the deal with that? And why do they get cut off and sometimes change directions? And how is that related to processes going on at Earth's surface? As it turns out, we're going to learn that rocks with these big waveforms that we can see here probably formed in an ancient desert where there were dunes active. And so those dunes are made of sediment, right? They're made of sand. And as we've seen already a little bit, we've talked about that sand that makes it up came from somewhere. It was weathered out of its original rock. And then it was later deposited in these dune shapes that we can see sort of the profile view of in this, right? Like, so these dunes might have at one point looked like that, right? If you continue all the way on up. And so we will see that we can interpret the structures in sedimentary rocks and different things about the sedimentary rocks to tell us that fact. So sedimentation in general, let's talk about really briefly and just mention some of the key details that we're going to see in this lecture. So sediments that make up sedimentary rock are produced on the Earth's surface as a result of processes we're going to call weathering. And that key part here, that it's on the Earth's surface, is going to be important because it's what allows us to use sedimentary rocks to tell us things about what was happening on Earth's ancient surface. But first, we're going to need to learn about the processes that actually put that sedimentary rock together. So we're going to talk about how sediments are eroded and transported. I like to use these terms and make them mean different things. Some people use them interchangeably. I don't like that, and you'll see why. And we'll talk about them as somewhat separate processes. But the rocks, once you weather the sediments, you turn a rock into individual bits and pieces. You start to move it away from where it starts. That's called eroding. And then you move those sediments through different places, transporting them. And then eventually they come to rest, deposition. And over time, they can get stuck together or lithified in a process of lithification to create a new sedimentary rock. So we'll see that sedimentary rocks, as I said, give evidence of ancient sedimentary environments where they formed. And we'll see that different environments produce different rocks. Each of these pictures is of a different sedimentary rock, and some of them have these big angular pieces or clasts in them. And we'll learn about breccias and what that indicates about how they formed and why those pieces are so angular versus other pieces that are roughly the same size, but that are much more rounded in a conglomerate. We'll learn about sandstones, where you can still barely see the individual grains making it up, even in the zoomed out picture. And we can see that they're arranged in these parallel layers, a lot like that first image, which was of a different kind of sandstone. But if they're sand-sized grains, they're likely sandstones. It's really hard to tell what this is from here. Maybe this is a siltstone, because we can't quite see the grains. Doesn't matter for now. And down here, we've got shales and mudstones with even smaller particle sizes. And that dark color often coming from organic matter trapped in them. We have some sort of evaporite over here that formed from precipitation of minerals. And then we've got this rock over here that looks like it's clearly made up of shell pieces, little fragments of shells stuck together, generally limestone, but the one specifically with these shells all combined together called coquina. We'll see some of these names again. It turns out that each of these formed in a different environment. And we'll learn how to interpret the environments based on the rocks that made them up. We'll also learn that not all environments form sedimentary rocks. So here's the lecture outline. We've got a lot to get through over the course of all of these sub-lectures. We're going to start with the classification scheme, give you a framework on which to understand everything else. Talk once again about composition and texture and about how we read those details for sedimentary rocks, much like we read them for igneous rocks, but we're going to use different terms here. And then we'll start to talk about interpreting sedimentary environments. Then later on, we'll get to stratigraphy, the principles that we use to interpret layered rocks, talk about sedimentary processes, those processes that we've already gone over very briefly. And then we'll talk a little bit more about sedimentary environments and interpreting some more of the details of those. Much like igneous rocks, the variables we're going to use to identify and classify sedimentary rocks are texture and composition. They're the main variables or the main properties used to classify these sedimentary rocks. But the terms are different than what we used before. So we had igneous terms and we had sedimentary terms. And we're not going to confuse the two. We can't confuse the two because they reflect different processes. And that's why we use texture and composition terms to classify sedimentary rocks, because it turns out they tell us something about the way in which these rocks were formed, similar to the way in which texture and composition terms tell us about the history of igneous rocks. But the processes are different, right? If igneous rocks formed from a melt, so we can use terms like texture terms, like, right, aphanitic and phaneritic, or extrusive and intrusive, or volcanic and plutonic, to tell us things about where the rock formed, above or below ground. Sedimentary rocks all form above ground and they don't form from a melt, so we're not going to use these same terms. Don't use the same terms. We also had composition terms, right? This was mafic felsic. For the most part, we're not going to use those to describe sedimentary rocks either. So what terms do we use? We'll talk about them. The composition terms, the chief composition terms that we're going to use anyway, are these ones. We can call a sedimentary rock's composition clastic, or chemical, or biological. And we'll see sometimes this one gets mixed in with those two. So let's talk about those briefly. Clastic means made of discrete pieces of other rocks. We call those discrete pieces clasts. That's why we call it clastic. Chemical sedimentary rocks, instead of being made of individual physical pieces like sand grains stuck together, they're made from chemicals which precipitated from solution. So that means they started out dissolved, right? They were probably things like ions in solution. We've talked about, for example, sodium and chloride ions. And there are various ways to make those minerals precipitate out of solution. They start out dissolved, and if you take out the water, you leave behind the ions remaining, and they can combine into what we call chemical sedimentary rocks. Biological just means any of these other kinds of rocks which come from living organisms. So that was your composition terms. Now let's start to think about some of the texture terms we will use. One important piece of that is going to be grain size. And in the clastic rocks themselves, we talk about the grain size because it tells us something about how energetic the water or the wind was that moved those particles around to put them where they ended up. So that's a little preview of why we care about the grain size and why that is what we use as our texture here. So composition clastic, we might talk about the grain size of those clastic rocks as their texture, and we get rock names such as shale, siltstone, sandstone, arkose, conglomerate, and breccia as these clastic rocks with different grain sizes. When it comes to classifying the chemical rocks, it turns out that while we can talk about the grain size and texture, really most of our classification comes down to composition again. Not entirely, but part of it. So all of these rocks, halite, we you'll recognize as a mineral. Gypsum, you'll recognize as a mineral. Dolostone, that's close to the name dolomite, right, which is a mineral. Those are all made of their constituent, the relevant minerals. So a chemical sedimentary rock that's made out of sodium chloride, it's all compositional, right? All of those terms are compositional. That's halite. And we have gypsum and dolostone doing that same work. Oolitic limestone is a special kind of limestone made of ooids, which is kind of about texture, but we'll talk about that. And then it turns out that we can talk about biological rocks such as limestone, chert, and coal too. But those are all down to their composition, right? Coal is dead plants. Chert is shells of organisms that actually precipitate stuff that's kind of like quartz. It's silicon dioxide, but it doesn't have the same crystal structure. So this is silicates. And limestone comes largely from organisms that precipitate carbonates. Particular calcite, that calcium carbonate mineral that we've learned. And as I said, in some cases, it's not obvious whether or not biology was involved in a lot of these. So you might see chert just simply called a chemical sedimentary rock. But it's likely that it had some biological influence. It can be hard to tell. Similarly, right, we see two kinds of limestone over here. Is it biological? Is it chemical? Well, it depends on how you want to classify it. We might say biological for limestone. We might say biochemical because it is also a type of chemical sedimentary rock. We're going to use biological more often to refer to these other two types. So we'll say biochemical or bioclastic when it is a chemical or a clastic rock with some biological influences. So if we take a look at those clastic rocks, it turns out that most of the particles that make up those clastic rocks are silicates, once again, right? Talked a lot about silicate minerals. And that's because, as we've said, those minerals are relatively resistant to weathering, especially quartz, but also some other ones that we'll talk about. Because most of those clastic, those sedimentary rocks that are made of individual pieces are made of silicates, we'll often call them siliciclastic sediments. Pieces made of silicates. If we look at those sediments, we can break them down by how big they are. So big pieces, they can range in size from 2 millimeters, which is maybe about the width of the writing that I'm putting on this slide, right? It's not very wide. If you pull out a ruler, you'll see that 2 millimeters is, maybe that wide, maybe about that wide, not much wider than that. So these are still tiny particles, and it goes all the way up to huge particles, bigger than 256 millimeters, which is a weird number to use, but that's on the order of 8 to 10 inches, we would start to call boulders. At any rate, these are all terms for big pieces. And you might see them used. The rock that they're going to make is conglomerate. So particle size, that's the texture term. Conglomerate, that's the name of the rock that they form. We'll see that sometimes this is called breccia, depending on how angular it is, which is another part of that texture. So I'll add that in there. Medium grain sediments, so 2 millimeters down to 0.062 millimeters. Basically, they're smaller than this, but they're still big enough to see, mostly with your naked eye, but also occasionally with a hand lens, which is kind of like a tiny, tiny handheld microscope that barely magnifies anything at all, but just enough magnification to see the smallest sand grains. That's how big sand particles are. Think sand on a beach, that's the size of a sand grain. And conveniently, they make a rock called sandstone. A particular kind of sandstone that has a lot of not only quartz, but also like orthoclase feldspar and stuff that forms in deserts because there's not a lot of water around, we might call arkose. So you might see that name too. So I'll throw that there. And then finer grain sediments might be called silt or clay. It's impossible to tell the difference between these just by looking at them. Turns out the way that geologists do it is if you have silt, it feels gritty on your tongue, and clay feels smooth on your tongue. So if you want to test some sediment, you check it like that, or you use more advanced techniques. I recommend not eating silt or clay because that can be gross, and it could be contaminated with heavy metals and whatnot. But you know, geologists have a reputation of being a little bit nuts, whether it's because they eat silt and clay or a cause of them eating silt and clay, I can't exactly say. At any rate, these are tiny particles, right? And they make rocks that we call siltstone or mudstone or shale or claystone. You might see some of those names too. We're just introducing them now, so you don't have to memorize it right away, but these are going to be repeated over and over again. And you'll see these in lab too. So make sure to start to contextualize that when you see it in lab. Think back to this lecture and think about the particle sizes as you see these names come up. Okay, so the rock breccia, big angular pieces. And it is a siliciclastic rock, meaning most, if not all of these pieces are made of silicates. So that would be called a breccia. Ones with much more rounded pieces are called conglomerate. And it takes some judgment to decide, is this an angular piece because it's kind of angular there? Or are these pieces more rounded, like this one here? Really, you want to take a look at the edges first and foremost. And you can see that even the edges of these sort of angular ones have some rounding to them. So you'd probably call this one a conglomerate. Certainly in comparison to the previous one, you would call this conglomerate. Big, rounded pieces. Again, siliciclastic. Sandstone, medium, right? Sand-sized particles, pieces. Can be rounded, can be angular. Certainly gets harder to tell when they're this small, but we'll talk about those two. It's often bedded like you see here, but it doesn't have to be. Pretty plain rock called sandstone. Shale, tiny pieces. Mostly siliciclastic, but there's some organic matter in here that gives us this dark color. And the shale breaks into these pieces. It's called what we call fissility. It's fissile. It breaks into chips, not really sheets, but like if you've ever seen shale, you know that shale breaks into these chippy pieces. Now, this section is called different environments for different rocks, and we've seen each of those rocks. Now, how does that depend on the environment in which they formed? We could look at an example profile going all the way from the mountains where the headwaters start and the stream is running down, and here the stream is moving fast. And then as it exits the mountains, right, it slows down and it starts to meander on very flat plains. Here, we might call it a river at this point, is slow. If you've ever gone hiking and you've looked at some of these mountain streams and you've looked into them, you've seen that the channels are usually filled with big chunks, cobbles and boulders, big pieces. That's related to the fact that the stream is fast there. And at its fastest, you know, in big storms, it can just barely move those pieces around. But for the most part, it's just, the stream moves fast enough that it lets small pieces pass and the really big ones stick around. Near the headwaters, but still kind of outside the mountains, it might be filled with gravel. Finer grains are still carried downstream. And then where the river is very slow, the channel itself is now just filled with sand grains. The water itself is barely carrying any of those sand grains. And for the most part, it's just moving very fine particles, silt and clay downstream. and the floodplain around it is covered with mud. And that resulted from floods. So if we think about this, we'll see that the speed at which the water moves, we can talk about the energy of the environment. Is what ties these together. Faster moving water carries bigger pieces. Slower moving water carries smaller pieces. So if the sediments that get left behind in these environments were to be preserved as sedimentary rocks, then the ones that formed in areas with faster water would have bigger pieces. Slower water would have smaller pieces. And that's the main way that we interpret the environment of siliciclastic rocks, based on the energy of the environment in which they formed. Switch it up a little bit and talk about a bioclastic, so made of pieces, but with a big biological influence, sedimentary rock that we call coal. In a place like swamps, where there's not a ton of oxygen around and the water isn't being mixed, pieces of plant matter can fall to the ground and decay only slightly before they're buried. So they don't react all that much. And once they're buried and they sort of squeeze some of that water out, they're probably called peat after tens, hundreds, thousands of years. But then over time, and with pressure, as you see here, pushing on it, pushing more of that water out, and some heat, as you go deeper underground, the temperature rises a little bit. And if you do this somewhat for millions of years, you turn your peat into lignite or subbituminous or bituminous or anthracite coal. These are all just types of coal. Coal is formed originally from plant matter that didn't quite break down before it got buried in big layers. Coal is old plants. So those are some of the key clastic rocks. We saw mostly siliciclastic, then we saw one bioclastic rock. Now let's talk about the chemical sedimentary rocks. So they form when minerals precipitate from water solutions. Precipitation is a type of crystallization that occurs from dissolved ions. We've seen precipitation before in one of those little videos I showed you, where we had the dish of salt water that was allowed to evaporate, and those ions combined and precipitated into new cubic pieces of halite. That's precipitation. So these typically form when water is what we call supersaturated. That means has too many ions in it. How does that happen? Well, just like in that dish, you can cause water loss by evaporation. If you said, took like a piece of the ocean, right, like an inland sea or something, and you cut it off from any water inflows, and then you started evaporating that water, you would leave behind salt deposits. Those are types of evaporite rocks because we've evaporated the water to create them. So that's one big class. Another way that we can cause there to be too many ions in one place, that we can cause supersaturation to happen, is biological activity. Some organisms deliberately pump these ions, the mineral components, into particular places that they need them to make their shells or to make their bodies, to make the substrates on which they live, like corals do. These tend to be creating limestone because the biological pumping that they tend to do tends to combine calcium ions with carbonate ions. There are a couple others where biological organization of mineral components can produce silicates like chert, but for the most part, this biological activity is going to create calcium carbonate, mineral calcite, which is the main component of limestone. Okay, so if we look at this, this is a diagram where we have some water with a little bit of dissolved salt, right? As this water is moving over the landscape, it's weathering the minerals that are there, and some of those components are going to dissolve in the water. And so most surface water has at least a little bit of dissolved ions in it. And that water might flow into this restricted lake here that has no outflows, right? It's in a desert. As that water is allowed to evaporate, the salt concentrates, it gets left behind. More and more of it will be there and it will precipitate. That's a result of it concentrating in this area as a result of evaporation. So which type of rock is this? Well, these are chemical sediments, right? Because they're forming from precipitation. And specifically, they're evaporites. Here's an example of one of those. So Death Valley, California. If you have ever visited there, you'll know it's a really strange landscape. One of the places in there is called the Badwater Salt Flats. And what we've got going on here is this restricted basin where water can't flow out towards the ocean from anywhere. So any water that flows in brings all of its dissolved ions. And how does it leave? By evaporation, right? Death Valley is generally the hottest place in the US. So sun's beaten down, it's evaporating this water. And what gets left behind? Ions. Ions that combine into evaporite rocks. Right, so a lot of this is probably halite. There might be some gypsum mixed in and some other salts. When we talk about the rocks that evaporites make up, we usually just refer, at least in this course, to the minerals that make them up. So an evaporite rock made of halite we'll just call halite, even though it's individual crystals, right? These cubic crystals of halite that you know so well at this point. As the water that they were carried in evaporates, leaves behind sodium and chlorine ions, combine into halite, we just call that rock halite. Gypsum is a similar one, but it's made of calcium and sulfate and actually a little bit of water in that crystal structure. They can precipitate in these very interesting ways. Like this one's called a desert rose. It's a very pretty combination of all of these blade or plate-shaped crystals that we can see outlined there that have all grown from one sort of central nucleus. They've all combined into this pretty shape that is reminiscent of a flower or a rose. It's pretty cool. Limestone is another example of chemical sediments. What was the unique thing about calcite? What was so easy to identify about calcite? Calcium carbonate. One diagnostic tool that we use was that if you put acid on it, it fizzes. It's because as you put acid on it, that calcium carbonate actually turns into water plus CO2, and that CO2 gas bubbles out. That's why you see the fizzing. It also breaks down the mineral because that carbonate gets converted into carbon dioxide. So if you put some acid on this rock, a bottle of acid, put little drops on, it would start fizzing, bubbles, bubbles, bubbles everywhere. Limestones are formed chemically, sometimes, often through biological action. Only occasionally does it not involve biology at all. But those organisms are putting together calcium and carbonate ions to build their shells, or in some cases, just as a result of their metabolism, whatever they're doing to stay alive, they produce this carbonate as sort of a byproduct, and it combines with calcium that's there and forms these layered calcium carbonate rocks that we call limestones. So, as we've said, limestones are sedimentary rocks composed of fine-grained calcite. You're not usually going to look at a limestone and see these nice rhombohedral shapes with the three nice cleavage faces that don't meet it quite at 90 degrees, like we talked about. So you won't necessarily see that, but you will see that if you put some acid on these rocks, they will fizz. So it's a good way to diagnose when you have a limestone. Here's another picture of a limestone here. It's got some interesting biologically formed structures that we can see. These formed in an ancient warm sea, or at least on the shoreline of an ancient warm sea, possibly. Without getting up too close to look at them, I can't really tell, but I expect, based on where I know these are from, that these are what are called stromatolites. It's a word you probably won't see too much in this course, but it's a word you would definitely see in historical geology. These are ancient biological mats that are made of bacteria that have all sort of coalesced into one spot and left behind these mound shapes made of limestone. So they were a major contributor to forming limestones, especially in ancient times. And you often find those in Tennessee. So if you're ever looking at limestone in Tennessee and you come across these sort of lumpy shapes amidst what is otherwise a pretty flat-lying or indiscriminately layered rock, it's probably a stromatolite. A lot of the formation of limestones happens in warm, shallow waters, and those waters tend to be nearest the equator. So one marker for things that are forming limestone today, that are laying down calcium carbonate, are these coral reefs. And if we look at where those are located, they tend to be nearer to the equator, which is right about there, at least in warm waters, right? So it's still pretty warm anywhere in this range. And because it's shallow there, these organisms that do it, a lot of them are photosynthetic, so they need light in order to survive and make their own food. So the shallow waters help that happen. The warm waters help biology to act much faster, just in general, right? You're much faster if you're not totally frozen. So these warm, shallow waters tend to be where you have coral reefs, tend to be where you form limestone too. So once again, we think about the sedimentary rock and where it formed. And we can start to tie the environments in which those rocks formed to the sedimentary rocks that we can see remaining from them today. Now, I've already mentioned, right, Tennessee has a lot of limestone in it. It's not in warm, shallow waters near the equator, but it used to be. Sea levels used to be much higher when there was no ice in Antarctica and when the continents were arranged a little bit differently. So that a lot of the rock in Tennessee formed when Tennessee was closer to the equator, was warmer, and was under shallow water. I point this out to note that environments today, remember, are not the same as the environments in which the rock formed millions or hundreds of millions of years ago. So limestone sometimes looks nice and pretty, like you saw. Here's another view of a different piece of limestone that can actually look dark in color. So don't use color as a diagnostic for limestone. This limestone still will fizz if you put acid on it. Sometimes you can have these fine layerings to it, just like you see fine layerings in sandstone or shale. The real diagnostic tool, though, is get your bottle of acid and put it on there. So another chemical sedimentary rock that I mentioned is chert. This tends to form, instead of big layers, it tends to form nodules, often inside limestone. So we'll find a lot of chert in Tennessee as well. And this tends to have often this waxy appearance to it, I say. It's not strictly a luster because we're not looking at a sample of a mineral, but it does look waxy, and it does have these curved breaks on its surface. And if you felt that, you would see that this surface too is pretty smooth and curved. Remember, that's conchoidal fracture. How did these things form? They actually formed mostly, and probably, we're not entirely sure about all cases, but these probably formed from different kinds of organisms that built shells out of silicon or silica instead. It's less common than making your shell out of calcium carbonate because it's a little harder to do. Silica doesn't dissolve as easily, so there's not as much of it available. And it's not a product of metabolism, but you don't have to worry about all that. Just know that chert is a chemical sedimentary rock made out of silica. Well, it doesn't fizz then because it's not made of carbonates. And it is pretty hard, right? It's easy to scratch other things with chert. Some other ones, right? Gypsum was a mineral that we've already talked about. Calcium sulfate, it's pretty soft. And halite, remember, it forms those cubes. And these two are evaporite deposits. So if we summarize our compositional term, clastic versus chemical, if we're breaking it into those two categories principally, we know clastic are made of clasts. Mostly, these are going to be siliciclastic, but not always, right? We saw coal is bioclastic, made of different pieces. And you can see the grains in them if they're large enough, right? Breccia, we could see the grains. Shale, we can't see the grains because they're microscopic. And we'll talk about how they're stuck together. They're cemented together. We'll talk about that in a bit. Chemical rocks, instead, are precipitated from solution, either just abiotically by evaporating water or through biological action. Because of what they're made of, right? So they're made of halite or gypsum or calcite. We talked about all those. The hardness here of those minerals is less than 5 for the most part. So these tend to be softer, rocks as well as minerals, except chert. Chert's pretty similar to quartz, so its hardness is high. Let's talk a little bit more about the texture terms, especially as they pertain to siliciclastic rocks. We won't use these same terms to talk about limestones, for example, because those formed in a totally different way. The observations that we make are of the grain size. Can you see them with your naked eye? Then they're up here with your eye. Woo. Silt and clay, you can't see without a microscope. And it has to be a pretty good microscope to see silt versus clay. These are gritty. These are pretty smooth feeling. And they form different types of rock. Conglomerate or breccia, depending on how angular those pieces are. Sandstone, if it's made of sand-sized grains, so small grains that you can still see, or siltstone or shale. So that's the observation that we make, right? This is your observation. Then based on that, we can make interpretations. And the interpretation in this case that we've already discussed is the energy of the environment. Or if we say it a little bit longer, it's the energy of the environmental transport medium. We described it in terms of water, but we can also talk about it in terms of wind. In a related sense, we can talk about it in terms of glacial ice, although energy doesn't work quite the same way just because glaciers are solid. But for the most part, we can talk about the energy that was used to transport the wind or the water that transported these sediments is what determines their grain size. And that's because more energy means you can move bigger pieces. That's the key. It's the physical connection. We've seen this already, but let's just repeat it briefly. Higher energy, bigger pieces. Lower energy, smaller pieces. And sometimes that environment is going to differ, right? Like, so in the channel, the water is always moving, so maybe it can move sand grains. But on the floodplains, water only gets there when it floods, and then that water is moving really, really slowly, and it takes a long time to drain away. Because it's moving so slowly, the finest pieces would get left on this floodplain, and that's why the floodplain is covered with silt and mud. Mud is partially clay. So once again, energy determines the particle size that can be moved by an environment. That allows us to read the particle size of the rock and figure out the energy, but that only works for clastic sedimentary rocks, because those are the only ones that form this way, by a transporting medium, moving pieces around. Other pieces of texture that we can talk about for siliciclastic rocks, mostly, grain shape. So that tells us the distance and duration of transport. Why is that? Well, if you start out with grains that are angular, right? They have rough, sharp edges. As you move those around, those pieces are bouncing against each other. Those pieces are rubbing against surfaces. Those pieces have longer for water or other chemicals to act on them and to start to dissolve and break those sharp edges down, so that over time you go from angular to rounded. There's some grain size change too, but for the most part, we think of the angularity or the roundedness, and we interpret that observation as the distance or duration of transport. Because the longer you do this, the longer you sand something, the longer you sandblast something, the smoother it's going to get. Grain sorting, that refers to how well size sorted it is. So if sediments are mostly all the same size, right? And even in very well sorted sediments, there's some size variation. But for the most part, these sediments are all the same size. And as you move down, you can see the difference between very well sorted and very poorly sorted. You know, this one's got a mixture of microscopic grains and huge grains the size of your thumb. This one, most of the grains are all roughly the same size, give or take 100, 200%. So what does that mean? Well, we interpret that in the same sort of way that we interpret grain size in general, except that it tells us about how consistent that energy is. So on a beach, the waves are always moving back and forth with roughly the same energy, right? On windy days, they're a little bigger. On calm days, they're a little smaller, but they're always moving about the same, moving back and forth, and they pull out all of those tiny pieces and they move them offshore, regardless of how much wind is happening. So beaches tend to have pretty consistent energy levels, and they end up with very well-sorted sand. Your beach sand is pretty well sorted. On most beaches, you don't have big cobbles and also mud patches all in the same place. Very poorly sorted sediments might come from something like a flash flood. So if a place like a mountain stream is prone to flash flooding, that water will move very fast, very suddenly, and it will pick up all kinds of sizes. And then that flash flood disappears just about as fast as it started, and it dumps all those sediments in one spot. If all that water slows down at once, it'll leave behind all these particles at once, and you'll end up with a very poorly sorted sediment. So in that situation, right, the flood is sometimes not there at all, and water is moving very slowly, and then all of a sudden it's very, very fast. So that energy level is inconsistent. On the beach, that energy level was consistent. And that's tied to the grain sorting. So if you ever want to look back and think about the important details here for siliciclastic texture, you can look at this summary slide. It just goes over grain size, the grain rounding, and the grain sorting, and what those interpretations are of these observations that we can use to tell us about the environment in which sedimentary rocks, siliciclastic sedimentary rocks, formed.